Okay. Do you have any idea about how many people are going to show up? At the moment, we've got two.
I will mention them on the group to ask them if they want to join or not.
Sure.
You know, it's a final period.
Yeah, that's no problem. So I'll just give it 2 or 3 more minutes.
Yeah, of course.
Very much. Okay, so good afternoon, all of you. So today I'm going to have a look at some of the test solutions. And, these solutions are not due to me. Samid gave me most of the solutions, but I did go into a bit more detail with question 2, which was the geometry question. And I'm just wondering, can I get up let's see if I have the questions in front of me. I think I can get them here on my OneDrive. So if you just give me a second.
If you wanted to send it on the chat, I can do it.
Yeah, I do have them. It's just a matter of
Oh, okay.
locating them. Okay, so do I have it here? Okay, that might be the quickest way of doing it. Inside WhatsApp, or actually, no, I think it would be quicker if I just do it here on my machine. So if you just give me a second, apologies. Okay, so that should be showing up there now in a second. Okay, so here is the test. Okay, so I'm going to start with question 2, which is the geometry question here. Now, so I'll just read it out. In a scalene triangle ABC, with the angle at A is 90 degrees, the tangent line at C to its circumcircle meets line BC at M. Okay, and I won't continue, but just a couple of things to point out here. Scalene triangle. A scalene triangle, now I wouldn't be immediately aware of what that is, but it means that all of the angles are different. So it means in particular that you don't get a degenerate case where the tangent line at A doesn't meet BC. So that's the first thing. So this is all angles distinct. The other thing is the incircle. And the incircle of a triangle, ABC, is the circle that's inside that just touches the 3 edges, like that. And so on. Isosceles, of course, means that it's got 2 angles are equal, which is, I guess, the opposite of scaling. Okay, so that's the question. You have access to those questions, so I'll go back to the solution. Okay, so there's a couple of little results that are relevant. So you're probably familiar with them, but they're worth highlighting. So these are all relevant to the way you solve this question. So the first one is that if you've got a circle, so here's my circle, and I've also picked an arc on the circle, which just means a segment. So you've got 2 points on this circle, and that defines an arc. And you've got an angle standing on the arc. This is called standing on the arc. So that's, in this particular case, it's this angle here. Okay, and I've called that angle alpha. And then you've got an angle standing on the arc, but at the center. So I've got the center here. And then you've got another angle here. And the main theorem here is that the angle at the center is twice the angle standing on the arc. And that means that if you move the point here to any other point along the circle, you'll get the same alpha. And this is very useful. So, sorry, my drawing program is acting up. So you'll also get the angle alpha here. So the alpha doesn't change as you move around the circle. So that's the first result, or theorem. So this is a theorem about circles. And so an extreme case is where the arc is half the circle, so it's a semicircle. Okay, so my arc in this case goes all the way from here to here, and we've got so in other words, we've got a diameter here. And so the angle here at the center, because the center is here, the angle is pi radians. So the angle at center is pi radians. And therefore the angle standing on the arc here is pi over 2. So the angle standing on a diameter is pi over 2 radians. So you're probably familiar with this theorem. And this is if and only if. So if it happens that you've got an angle inside a circle which is pi over 2 radians, then that angle must be standing on a diameter. And that's precisely what we have in the question. Okay, so I hope both of those circle theorems are reasonably familiar to you. Well, that's really one theorem. Okay, so the second thing I want to point out is about the in-circle. So how do you construct the in-circle? So I've got a triangle here, ABC. And so how do I construct the in-circle? Well, I have to construct the in-center, which is the center of the in-circle. And the in-center has the property that, actually, I've forgotten the formula, but if you drop a perpendicular to each of the three sides, that the three, what would you call these? These three line segments have the same length. And what that means, if we look at A, and what that means for A, it means that the in-center is on the angle bisector there. So you've got an alpha and an alpha, and that means essentially that this triangle here, which I've written as AST, this is an isosceles triangle. So you've got an angle beta and an angle beta, which are equal at those two corners. Okay, so that's another point I want to make, that this triangle here, which I'm just going to move it about there to highlight it, that's an isosceles triangle. Okay, so that's also relevant to this problem. Okay, so Lean, you were asking me about visualizing this problem. So here is the drawing for question 2. So question 2 diagram. Okay, so if I briefly run through the way it works, you've got an angle at A is 90 degrees. So I'll just highlight that in red. So you've got a 90-degree angle here. And that means that ABC, well, the angle CAB is standing on this diameter of the circle here. Okay, so that's kind of the meaning of that 90 degrees. So in other words, CB is the diameter of a circle. Okay, so that's the first thing to point out. I'll just label things as I go along. So CB is the diameter of a circle containing A, B, and C. And that's because of the angle at A is 90 degrees, or pi over 2 radians. Okay. So then the circumcircle, the line BC.
Mr. John?
Yes.
Karim asked you a question on the chat. He asked, I have a question about the geometry problem.
Okay, sure.
Can you tell Karim? If you can't, I can read your chat.
Yeah, if you can read it, that would be great. Can you read it out? Sorry, I'm not hearing anything.
Karim, I think he has a problem with the mic. I asked him to type his question.
Okay, I'll have a look at the chat then.
Okay.
So where's my Zoom? Okay, so we've got, oh, where do I look at the chat? Oh, here. Can you type? So Karim says yes. Okay. So I'm waiting for Karim to type. Karam, apologies. Oops. Okay, so still don't have anything from Karam.
Maybe he's still typing. If you want, when he's finished typing his question, I will interrupt you.
Okay, thank you. Okay, so I'll go back to the notes. So so far we have that BC is the diameter of the circle that contains A, B, and C. And then I think the next thing is that the tangent to the circle at A. So we've got the tangent line, and it's going to meet BC at the point M. Okay. And the in circle, which is here, this is the in circle, that's going to touch AC at S. And it's going to touch AB at R. Okay, so from what I said previously, we've got a nice little isosceles triangle here. So this is isosceles. Okay, and then SR touches the tangent at U, and it also intersects BC at N. And the problem is to prove that UMN is isosceles. So this is the triangle of interest here. And I think you can see that we're basically trying to prove that this angle and this angle are the same. So I'll just put question mark. Can we show that those two angles are the same? So Karam still hasn't typed?
No, he's still. I told him if you want to write it in Arabic and I will translate. I'm not sure if he typing or not. But
Okay. So I'll just continue for the minute.
yeah.
Okay. So I'm going to start labeling some angles based on basically what I've just been saying. So here's my diagram, and I'm just kind of simplifying the diagram, and I'm just going to blow it up. And the labels are going to be as follows. So I've got that red angle in there is a 90 degrees. And I've got another 90-degree angle here. So maybe I'll do it like this. We've got 90.
Typed.
So he's typed.
Yeah, he asked, I want to know if I take a complete mark or incomplete mark in the geometry problem, because I think that my argument doesn't consider all cases.
So I'll have a look at, let's see, I think I have the marks. So for the geometry, okay, do I have the complete list of marks here? Yeah, Karam, you got 10. You got complete marks for the geometry. Okay, because I think I said at the beginning that no one got this out completely, but actually, Karam, you did. Okay, so I hope that answers things. Okay, will I keep going, Leanne?
Yeah, you can keep going. Actually, Karam can't hear anything from the meeting, so I typed him that he got a complete mark.
Oh, okay, okay, and give my regards as well. You can say we're all thinking about everything that's happening. Yeah. Okay, yeah. So I go back to my diagram, and because of this argument with the in circle, so maybe I'll just mark that I have the in circle here. So there's two things. First of all, we've got a 90-degree angle here, which I'm going to mark in red. So that's the angle at A. And then we have another 90 degrees, which is this angle. So this is kind of hard to, maybe I'll use this convention that you sometimes see, which is you mark a 90 degrees by putting this kind of box. So that's 90 degrees, but also that is 90 degrees. So we've got two 90 degrees there. And then it's easy enough to see that that means that if I mark this angle as alpha, let's see if I can mark it better, alpha, we also get an angle alpha here.
John, Karim said that he didn't prove the order point M and U. I discussed it only possible one. So he wondering how he got a complete mark.
He didn't discuss the
M and N and U point.
Okay, so myself and Mark and Tashin, who's in California, and Samit met, I think it was a week ago, to discuss, to finalize the problems. And so Tashin thought that the answer was complete, that basically all the elements of the answer were complete. Now, as far as I know, Tashin is going to be doing some advanced training for the people on the team. And so I can ask him, I'll ask Samid to get Tashin to send his comments to Karam. That might be the most efficient way.
Okay.
Okay. Okay, so back to this diagram. Because of this argument with two right angles at A, so one of them is because we're given that in the triangle ABC, we've got a right angle at A. So we've got the angle BAC is 90 degrees. But we also have that the angle DAM is 90 degrees. Now here, D here, I don't think that was part of the question, but D is the center of the circle ABC. Okay, and the reason for that is because AM is a tangent line. So therefore it's at right angles to the radius here. So this is the radius of the circle. And that allows me to say that these two angles here are equal. And I'm calling those angles alpha. And it might actually even be clearer if I got rid of these lines. So I've got an angle alpha and an angle alpha there. But I also know that SAR is isosceles. So triangle SAR is isosceles as S and R are the feet of the perpendiculars to the in-center of triangle ABC. Okay, so we have an angle beta here and an angle beta here. And sorry, I'm just trying to make it, oops, this is hard to draw properly. I'll draw it big and then we'll have a look. There's beta and there's beta. So I'll blow it up. So we've got the angle beta there and the angle beta there. Okay, so it gets a bit crowded here, but now we've got opposite angles. So we've got an angle beta here because it's an opposite angle to the beta I've just drawn. Okay, I have to draw big as well. Oh, this is misbehaving. Okay, so that's because of opposite angles at R. So now I've filled in various angles. Oh, there's another thing as well, which is important, is that triangle SAR is a right angled. And isosceles. So that tells me that beta is actually pi over 4 or 45 degrees. Okay, so let's get rid of beta and put in 45 degrees. Or maybe I shouldn't do that, but anyway, this is pi over 4 and pi over 4. Okay, so what else can we say from this diagram? So, oh yeah, there's another thing we can say is we have another isosceles triangle here, namely triangle ADC. This is isosceles because AD equals DC, because these are the radii of the triangle ABC. So we have this nice isosceles triangle here. ADC. So we can put in an alpha over here. Okay, so now we've got a load of angles in our diagram. We've got the angle alpha, which we don't know what it is, but we also have this angle beta, which is, it turns out, is pi over 4, or 45 degrees. Okay, and now I'm going to move on to this angle here. And you have this nice result that this angle at D is going to be the sum of the interior angles in CAD, because together with this angle, it adds up to 180 degrees. So the upshot of that is that we can actually label this angle as 2 alpha. Is all of this making a little bit of sense? I know it's crowded diagram, and
No, it's clear till now. Thank you.
okay, so what else can we fill in here? So we've got pi over 4. So we have, let's see, how does this work? So I'm not sure if that was important. So we've got 2 alpha. This angle here is going to be, because you're taking alpha away from 90 degrees, it's actually pi over 2 minus alpha. So if we look at this angle, whatever it is, it's going to be the sum of pi over 2 minus alpha plus 2 alpha, because it's the sum of this angle here and this angle here. And therefore, the minus alpha plus 2 alpha becomes alpha. So I can just replace that by pi over 2 plus alpha. Okay, so that just requires a little bit of argument there. So now we've got RBN, and we've got 2 angles in RBN. We've got pi over 4, pi over 2 plus alpha. So this angle, the third angle in that triangle, is going to be pi over 4 minus alpha, because the sum of those 3 angles is 180. Okay, but now we do an angle chase inside ARU. So we have this is pi over 4. So this is this angle at R, I think it's called the supplementary angle. I'm not sure what it's called. This angle here is going to be 3 pi over 4. And we've got our alpha here. So this angle is going to be pi minus 3 pi over 4 minus alpha, which is pi minus alpha. And therefore, this angle is also pi minus alpha. Have I got that wrong? I've got pi over 4 minus alpha and pi over 4 minus alpha, because the sum of this angle, and this angle has to be 180. Okay, and we have opposite angles, so you can see that I've shown that we've got an isosceles triangle here. Okay, so I think maybe I should summarize this as saying that there's a couple of obvious angles that you fill in. So the first obvious angle is this pi over 4. You have to give an argument that these are pi over 4s. I've given a name to alpha here, and then you try and chase alpha down which angles are alpha, using various arguments. And then it's called angle chasing, where you look at sum of angles in a triangle being 180 degrees, and you fill in angles as you go, and you can eventually find that UMN is an isosceles triangle. Okay, so maybe I've just given you an indication of how to solve this. I know it's hard to keep track of these arguments. So I'll put this up in the, I'll give it to Samid in PDF form, and he can distribute these notes to you.
Thank you so much.
Okay, so there are probably loads of questions you might have about this. I feel this is a difficult problem to explain, but it requires these elements at least. Okay, so the idea of the angle standing on an arc, the fact that you have the diameter of a circle, and then what happens with the in circle, and the sort of isosceles triangles you get there, and then the rest of it is an angle chase. Okay, so that's probably enough on question 2. So if you don't mind, I'll move on to question 1, which was a very nice question. Okay, so question 1. Now, I think the trick
Can we check problem 4 first?
Sorry, can you repeat that question?
Can we check problem 4 first, please?
Problem 4, okay, sure. Oh yeah, okay. This is also a nice question. Okay, so let's see if I can bring it up, just to remind you. So this is problem 4. Find all primes p for which there are positive integers x, y, and z, such that x to the p plus y to the p plus z to the p minus xy and minus z is a product of exactly 3 distinct prime numbers. Okay, so I'll rephrase this as an equation, first of all. So find all primes p such that there are x, y, and z, which are integers and primes, distinct primes, q, r, and s, say, such that x to the p minus x, I'm rewriting it like this, minus y to the p minus y, z to the p minus z equals q or s. Okay, so some comments about this. So a typical way you look at these kind of Olympiad problems is you do a bit of experimentation. And in this case, the experimentation, an obvious way to proceed is to look at the case where p is a small prime. So when p equals 2, you're looking for x squared minus x plus y squared minus y plus z squared minus z is a product of 3 primes. And there's an obvious solution where you take x equals 6, y equals z equals 1, because then you get 30 plus 0 equals 2 times 3 times 5. We can do the same thing with p equals 3. In this case, you take x equals 3, y equals 2, and z equals 1, because you're going to get 27 minus 3 plus 8 minus 2 plus 0, when z squared minus z is 0. So we're going to get 24 plus 6, which is again 30. And then finally, for p equals 5, it turns out that if you take x equals 2 and y equals z equals 1, you're going to get 32 minus 2 plus 0 plus 0 equals 30. Okay, so with a bit of experimentation, you can find 3 solutions. So remember, the focus is on which primes. So the primes in question are p equals 2, 3, or 5. You can find x, y, and z. So at this point, maybe you do a bit more experimentation. You don't find any results for p equals 7, and you kind of wonder what's going on. So what's going on is the following. We have the following important fact, which is completely non-elementary. It says the following: if p is prime, then p divides x to the p minus x for all integers x. Does anyone know the name of that theorem?
Yeah, Fermat's little theorem.
Fermat's little theorem, that's right.
Abdullah typed in the chat little friends, something like that. Yeah.
Something like that, yeah, Fermat's little theorem. So this is a very famous theorem. Of course, Fermat's last theorem is completely different and much harder. Fermat's last theorem was proved by Andrew Wiles and his student, I think, Taylor, in about 1995. So it was a famous conjecture for hundreds and hundreds of years. But Fermat's little theorem is not so hard to prove, but I'm not gonna go into the details of the proof here. But the upshot of that is that that p divides x to the p minus x plus y to the p minus y plus z to the p minus z for all. So in other words, we can assume that one of the 3 primes on the right-hand side is p. Okay, the next thing to note is that, so let's assume we've dealt with the case p equals 2, 3, and 5. So assume that p is greater than or equal to 7, and it's prime. The key thing here is p is odd. So you can show the following. X to the p minus x is even because p is odd. Because if x is even, then any power of x will be even, and when you subtract an even number from an even number, you get an even number. Another key fact is that because p is odd, x to the p minus x is divisible by 3. And just to see this, if we look at values of x modulo 3, and we look at the powers of x, so if I have x squared, x cubed, x to the 4, x to the 5, I'm just establishing a pattern here. So the possible values of x will be 0, 1, and 2 mod 3. Then x squared mod 3 will be 0, 1, 1. X cubed mod 3 will, of course, be 0, 1, 2. And x to the 4 mod 3 will be 0, 1, 1. And then x to the 5, 0, 1, 2. X to the 6, 0, 1, 1. So the pattern is that x to the n minus x is divisible by 3 when n is odd, e.g. n equals p is an odd prime. Okay, so the upshot is what we have is 2 and 3 divide x to the p minus x. And hence, 6 divides x to the p minus x. So what we're looking for is, so we must solve x to the p minus x plus y to the p minus x plus z to the p minus x minus z. I don't know where I'm getting my x's from. Y to the p minus y plus z to the p minus z. We have the primes 2 and 3 have to divide, and also p divides, so it's 6p. Okay, and there's probably plenty of ways of proving this, but the easiest one I think is the following. Note, let's see, in the official solutions, I'll just go back to them. Yeah, so there's you can prove the following by induction. So I won't go through the details, but so k greater than 5 is an integer. Then you can show that 2 to the k minus 2 is greater than 6k. Okay, so you prove that by induction. And then so you've got 2 cases. X equals y equals z equals 1. Then you get no solutions. You check that. Otherwise, you have x greater than or equal to 2. So x to the p minus x is going to be actually greater than 2 to the p minus 2. And therefore, x to the p minus x is greater than 6k, so no solutions. Okay, so the key thing is to prove, which I'm not going to do, but to prove by induction, that 2 to the k minus 2 is greater than 6k. So just to reiterate, you find your 3 solutions, p equals 2, 3, and 5, and then you try and prove that there are no other solutions. And you do that by noting that for p and odd prime, x to the p minus x, so each of the terms is divisible by 6, and therefore the sum of the 3 terms, x to the p minus x, y to the p minus y, and so on, is 6p. And then you show that that's impossible for p greater than 5. Okay, so that's the end of my discussion on that. So I'm going to quickly move on to question 1, unless I have any questions about that. Okay, so I'm taking silence as agreement. So I'll move on to question 1. And question 1 was probably the easiest question. So where I'm trying to bring up, what am I trying to do? I'm trying to show you the question. So find all functions from the positive integers to the positive integers, so that the value of the function is a perfect square, and then you've got this functional equation. Oops. Which I don't, this is the functional equation here. Okay, so f of m plus n is f of m plus f of n plus 2mn. Okay, so I'll go back to this. Now, the trick here is, so by guesswork, whatever that means, f of n equals n squared, and a few of you guessed that this is a solution. And the reason for that is that if you look at f of n plus n, you get n plus m squared, which is n squared plus m squared plus 2nm, which is f of n plus f of m plus 2nm. And that's the functional equation satisfied. So now the difficult part, that's the easy part. The difficult part is showing that this is the only solution. So next, do a bit of, again, the way to tackle these is to really do a bit of experimentation. So what do we know? I'm going to set R to be f of, well, R squared is f of 1. So R is some positive integer. So that's, I'm defining R to be that. So we have f of 1 is R squared. What about f of 2? Well, f of 2 is f of 1 plus 1. And then using the functional equation, this is going to be R squared plus 2. So that's 2 R squared plus 2. Sorry, I can write it like that. Yeah, was there a question there? No, okay. So f of 3 is f of 2 plus 1. So that's f of 2 plus f of 1 plus 4. And you can rewrite this as 4 into 2 plus R squared. And if you keep going, sorry, that was, I made a mistake here. That should have been equals. And I've, oops. So you get f of 3 plus f of 1. And in this case, we get 3 by 2 is 6. And you can rewrite this as 3 into 3 plus r squared after thinking about it a bit. Sorry, not 3, but 4. So what have I done here? So no, I've written this the wrong way. So let's just go back over this. So we have, apparently, let's just see if this makes sense. R squared plus 2 into r minus 1. No. It does not make sense. No, here's what you get. You get 4 plus 2 into r squared minus 1. Okay, you got the 2r squared, and then 4 minus 2 is 2. And then you can do the same thing with the second one. It turns out to equal 9 plus 3 into r squared minus 1. So if I think about that, okay, I'll give you the general rule, which you can prove by induction. Okay, so I guess there's a little bit of work here in even coming up with the correct formula. So by induction, you can prove the following. F of n is n squared plus n into r squared minus 1. So let's just check that this satisfies, that we can prove it for, if we prove it for f of n, we can prove it for f of n plus 1. So the inductive step, f of n plus 1, we know is f of n plus f of 1 plus 2n by 1. So I'll substitute for f of n here. And it should be the case that this is n plus 1 squared plus n plus 1 into r squared minus 1. Okay, so I'm confident enough that you can check yourselves. Okay, so I don't want to go too much over time, so you have to prove that inductive step. Okay, so we have this general property, and we need to show now that r equals 1. So in other words, f of n is actually n squared. So how do we do this? Okay, so one of you gave me this argument, which I think is very clever. So very clever trick. By the way, I can rewrite this. Actually, a better way of writing this is the following. Oh, okay. No, I'll leave it like that. So so here's what I do. I set S is equal to r squared minus 1. So f of n is n squared plus ns, which I rewrite as n into n plus s. Okay. Now let P be a prime with P greater than S. So we know that there are an infinite number of primes, so we can always find a prime that's bigger than any given integer. So we have f of P is P into P plus S. Now, this is supposed to be a square. So by unique factorization, because it's a square, P has to divide P plus S. So P divides S, but P is bigger than S, so S equals 0. So r squared minus 1 equals 0. So r squared equals 1. And there we're done. Okay. But the key thing is this equality here, and there are probably many ways to proceed. From here. Okay, in showing that r is 1. Okay, and I mean, you've given me an hour of your attention. I can keep going with the last question, which is the combinatorics question. So unless there are any questions there.
No, it's all clear.
Okay, so question 3. And question 3 is, if I can bring it up. Okay, so we've got these funny tiles here. So basically we have to tile, we've got 2n by 2n tiles. And we tile them with these patterns of tiles, and they always, it wasn't really clearly stated, but these are the midpoints of the sides. So these tiles always line up with the tiles beside them. And so you get these paths. And you're asked to find the least possible number and the largest possible number of paths that are formed. Okay, so I'll very quickly give you the most number of paths and the least number of paths. And I guess you would discover this by experimenting. So the least number looks something like this. You've got the paths go like this. And if you think about that, you get 2n paths. Because, is that right? No, you've got 4n paths. Because you've got 2n of them meeting here, and then 2n of them meeting here. So that's a total of 4n. So that's the least number. And then the largest number, you basically construct them as follows. Apologies for my terrible diagrams. You can have corner paths like this. And then along the boundary, you've got paths like this. I don't know, I feel there's something very maybe Islamic or Arabic about these tiling patterns. So, and then you've got all these interior patterns.
Yeah, the Islamic history is rich with shapes and geometric.
Yeah. This is, you're not allowed to represent figures, is it? Or Muhammad. And so there's a lot of emphasis on patterns.
That's right.
Yeah. Okay, so you basically have two types of paths. You've got 4 corners, and the path is length 1. And then you've got all other boundary paths, which have length 2. And then you've got the interior paths. And these are basically squares, and they've got length 4. So this is kind of, each path has kind of the minimum possible length. So you've got the maximum possible number. By the way, just an interesting thing on the tilings is, I think, people have looked at the tilings in various mosques, and you may know of this aperiodic tiling called the Penrose tiling. It's aperiodic. You can look it up. So it's due to Roger Penrose, who's an English mathematician. And there's a very funny story about it being used for toilet paper. But anyway, I think someone has discovered an aperiodic tiling in a mosque from like 1,000 years ago. So, which is quite interesting. Okay, so the maximum possible number of paths, and if you count them, okay, so I won't go into the details, but you can count for this pattern here, where you fill in the tiles like this, over here, the number of paths is 2n squared plus 2n plus 1. So if p is the number of paths, what you need to show that p is somewhere between 4n, which is the smallest number, and the largest number, which is 2n squared plus 2n plus 1. Now, I think a few of you guessed these two limits, but it's hard to give a completely rigorous answer. So I'll just sketch the answer. So for the lower bound, well, let's see. The total length of all paths is 8n squared, because you've got length 1 from each tile, or is it length 2 from each tile, and there are 4n squared tiles, and each gives length 2. Okay. So the boundary paths so you've got at most 4 of length 1. These are the corner ones, where you just have a corner and you have a path that goes like that. And all others the boundary paths have length at least 2, because you can have a path that goes like that, but you could also have boundary paths that are much longer. So the total length of I'm probably going to fluff this explanation, but basically, if all paths are boundary, meet the boundary, oh yeah. So yeah, if all paths meet the boundary, and we've seen an example, well, there are, what's the total circumference? The circumference is 2n by 4, so there are 8n tiles on the boundary over 2, which is 4n such paths. So from this argument, we get that P is at least 4n. Okay, so that gives the lower bound. For the upper bound, so we take B to be the number of paths meeting the boundary. And therefore, I'm going to call C the number of interior paths. So on the one hand, B is 4n from the argument above. B plus C is the total number of paths. So C is P minus B, which is P minus 4n. And what we get is the total length, which is 8n squared, is greater than or equal to the 4 corner ones plus the 2 length for every boundary path that's not on a corner. So this is corners, non-corner boundary. And then 4 times C, this is all the others. And you plug in values of B and C in terms B, and you get something like 8n squared is greater than or equal to minus 4 minus 8n plus 4p, and rearrange that, and you get p is at most 2n squared. It's 2n plus 1. Okay, so sorry for going so quickly here, but that's basically it. You've got a calculation which isn't so hard, which basically you get an estimate for the lengths of various types of paths. So the key thing here really is that you pay attention to the paths that meet the boundary, and then the interior paths that don't meet the boundary. And then you need to have some way of showing that these two extreme configurations give you the upper and the lower bounds. Okay, so I've taken up quite a lot of your time, and thanks for your attention. If there are any questions about that, I'm happy to answer them.
Thank you, Mr. John. It was super clear.
Okay, and So I think I'm hoping, Mark, it depends on whether you think this is useful, but you can discuss this with Samit. So Tashmet is going to be doing some advanced training, and Mark and myself are willing to, if people are interested in, just continuing some kind of training, even for people who aren't going to Bath this year, just for next year or whatever.
No.
Hello?
I guess someone who entered and just leave. I'm not sure.
Okay. So we finished the meeting here now.
Yeah.
There's no questions as far as I can tell, or
About something that you mentioned right now, talk to Somid. I guess he will send us a message on our group. Maybe the other participant interested, and I will see if I'm interested or not.
sure. Okay. And maybe if you want to discuss with him what would be most useful, if you are interested in further training sessions, maybe suggest to him some topics so we can be a bit more concentrated on how we do this.
Yeah, of course.
Okay, listen, thank you all for your attention, and hope you all have a good week.
Thank you, Mr. John.